This is Mrs. O'Neill for AP Chemistry, Chapter 19, Section 7, Free Energy and the Equilibrium Constant. Should have watched that intro lesson on how these two are related to each other. Here are my notes. He talked about how his last many videos dealt with thermodynamics, and it also dealt with delta G, the amount of free energy available in the products and reactants, and the reaction occurring as we move from those reactants to products. So again, here is that diagram that shows us here's our reactants, the minimum amount of free energy that's available to make those products. So equilibrium, he reminded us that it was a measure of the concentration of that ratio between products and reactants. So how are delta G and K related to each other? They're inherently tied together by this information, okay? So really by this algebra equation of how delta G and the natural log of K are together related. And then he's also going to talk a little bit about some biological systems. So delta G and K can be related with this equation that is also on your reference sheet. So he gave you some examples here. He said if we have a positive delta G, positive free energy, we're going to have a negative or a very, very small, I should say, K value. But if our delta G is negative, we're going to have a large K value. Well, what does that mean? He reminded you that if a K is greater than 1, it's going to favor products. And that should make sense because if delta G is negative, it's going to be spontaneous. It's going to form those products on its own. So why is this important? He gave an example of cellular respiration, and he talked about these gears kind of moving and working together in a coupled reaction. So we have a big gear that has lots of energy, and we have a small gear that has little energy. But you need the two of them together in order for respiration to work properly. So onto your notes packet. In this section, you're going to write how the standard free energy change for a chemical reaction can be used to calculate that equilibrium constant, and of course vice versa. So here's that relationship. Again, it's on your reference sheet. And by the way, pause, fill in the blanks, and then play to hear my words, as I always say. So we want to remember if delta G is equal to 0, K is equal to 1, and you have the system at equilibrium. So here it shows you exactly what everything is as far as that equation goes. So this is that relationship again. This is that diagram where you have reactants, you have the minimum amount of energy, and you have your products. So again, it's that relationship between all three. So that relationship between how much delta G you minimally need, the equilibrium constant, and of course that equation on how delta H and delta S, according to temperature, is all related to each other. I thought this was interesting to, again, make sure you're understanding that a positive delta G is going to be a very, very small K, and that should make sense. These are not going to be very spontaneous because they favor the reactant side, where if you have a negative delta G, you're going to have a rather big K value because it favors the product side. In other words, it's going to be more spontaneous on its own. So here's an example dealing with that equation. So this is an example, and there are two practice problems. So go through the example with me, and then those practice problems you might want to pause and see if you can do them on your own. So they're giving us a K value, they're giving us a temperature, they're telling us that we want to find the delta G of the formation or the delta G of the reaction, right? If we're forming this N2H4, we're really finding the delta G of the overall reaction. So since delta G formation of N2, because if we're forming N2 in the gas form, it's really 0 because that's its standard state. Same thing with hydrogen, that's its standard state. We're really looking for that reaction. That's kind of what I just said before. So we're going to use this equation. Instead of using products minus reactants to find delta G that you saw previously, we can now use this equation, especially if they give us that K value. So there's our K value, there's our T value, and now we're going to plug and chug. Just as a reminder, remember temperature needs to be in the Kelvin unit. So hopefully you can get this, and maybe you want to pause the video and see if you can put it into your calculator correctly, especially with that natural log. And you should have gotten this as your answer. And we also want to remember this is going to be in joules because of the R value, the R constant. At least I use the 8.314, so that's going to be in joules. But we want to remember that the delta G usually is in kilojoules per mole. So we want to make sure we're understanding that. And notice here we have a positive delta G. Does that make sense? We have a rather small, really small K value. So we should have a positive delta G because that's not going to happen spontaneously on its own. So here's our practice problem number 1. Again, if you want to pause, see if you can kind of plug and chug. This one's a little trickier, but give it some thought and see if you can do it. Okay, so again, we have a positive K value. We have a negative delta G. That should make sense. If this is positive, that means it's larger than 1. It's going to favor the product side. It should be spontaneous, and this shows that to us. So negative 25 kilojoules or negative 25 kilojoules per mole. You could look at it either way. Here's practice problem number 2. So here I'm giving you the delta G values. Very interesting because all I say is calculate K. Now we're going the other way and we want to calculate K. I guess this was the tricky one, not the one before. That one's basically the same as the example problem. But here I now give you the delta G's of the 3 individual substances. So here we're going to do our delta G first, products minus reactants. And what's really nice about this reaction is all the coefficients are 1. So we don't even have to multiply any of those numbers by anything. So then we're going to use that delta G equals negative RT, natural log of K, to find K. So again, see if you can figure out that information and then plug and chug and see if your number comes the same as mine. So that's our delta G value. Now we can plug and chug into our K. We want to find that natural log of K, and then of course that anti-log. So again, see if you can put it into your calculator correctly. And again, you need to change those kilojoules to joules. That makes it a little tricky because you're using that R constant in the joule unit. You definitely need to change those kilojoules to joules, otherwise you will not get the right answer. So your natural log is there, and then can you take that anti-log and get 3.6 times 10 to the negative 9. And again, this is a small k and a positive delta G. Those go together, so that makes sense. So your closing video, very briefly I'll go through this because it was the driving non-spontaneous process, deals a little bit more with your biochem. So those of you taking AP Bio next year, this might be really good and informational for you. So again, a non-spontaneous process will not be able to occur without external energy. However, if we apply energy and enough energy, we can make it go, right? We have to force that order. We have to force it to go back the other way. So this would be considered a thermodynamically non-favorable process. So again, delta G, if delta G is greater than 0, it's not going to be spontaneous. If it's positive, it's going to take too much energy to get all the way up there. So how do we lift that ball over the hill? How do we get how do we get there? How do we get from a non-spontaneous reaction to make it go where we want it to go? Well, there's going to be 2 ways. One way is to add energy from an outside source, like electricity, like your rechargeable batteries, or the sun, like photosynthesis. Remember that those green leaves on those trees will not grow unless there's enough sun energy in order for that process. And the other one would be to couple it with a spontaneous reaction. So here we have 2 hills. We're trying to get this yellow ball over the hill, and it's not going to work. But if we have a reaction like this blue ball, if this blue ball comes rolling down with enough energy and enough force, we can cause that reaction to make this reaction have enough energy, have enough force to get over that hill. So that's kind of what he said. Let's couple it. So we're going to take that blue circle and we're going to go down that hill, and it's going to give it enough energy or enough force to get that yellow ball up to that non-spontaneous reaction to make it go. Again, gave us a nice flow chart. And here again, he mentioned that photosynthesis and that reaction coupling, like he talked about those big and small gears with that ATP. So again, here he's talking more about those batteries and how they run out. And of course, plants and making it green, and energy coupling. So if we compare a non-spontaneous reaction with a reaction that would be spontaneous on its own, that's called coupling. You're kind of putting them together to make the reaction do what you want it to do. So again, he talked a little bit more about inside of our body, and this is more about your AP Bio or your biochemistry information. So hopefully that makes sense. Again, with our nerves as well. There's the biochem process I was talking about. Okay, we will see you in class.